So good morning students. So I welcome you in the lecture of linear integrated circuit. So in this lecture we will discuss about the inverting and non-inverting operational amplifier. So the previous lecture, what we have discussed is uh, characteristics, that is ideal characteristics and practical characteristics of operational amplifier and block diagram of operational amplifier. If you have not watched that video, so please go to the playlist and you can watch the entire video, and you can again we'll start with this inverting and non-inverting amplifier. So what exactly mean by inverting and non-inverting amplifier, that I want to see. Suppose I'm talking with you, okay. So with the same intensity, if I want to talk with the our auditorium, none of auditorium auditorium is there. If I want to talk with that auditorium, then what will happen? My voice is not audible to the last person. It might be good for the first row or second row itself. If I want to convey my message to the entire hall, then what I have to do? I have to use the amplifier. So what exactly mean by amplifier? So amplifier will increase the strength of the signal. That means what? It will amplify the signal. Okay, the process is called amplification, and we have to see the amplifier in this case. So this is my operational amplifier. This is a, what can I say, symbol of operational amplifier. There are two inputs. First is my inverting input, and second is nothing but my non-inverting input. Okay, and we are taking output across this one, and this is nothing but my supply pin, positive supply and negative supply over there. So in the comment box, can you comment that what is the supply voltage range of operational amplifier? So use the comment box and you have to answer the question that what is the supply voltage of operational amplifier. So minus how much voltage is required and plus voltage how much is required. So in this case, if we are giving input to the inverting input, this pin number 2, this pin number 2, if you have not watched the videos of pin configuration, you can watch the videos of pin configuration also. I have explained each and everything in that one, how to use and what is the pin numbers. So if you are giving voltage to the inverting input, so V2, and you can ground this V1, then what will happen? The configuration is called as inverting amplifier. And the second case, when you are giving the input to this pin and by grounding this pin, inverting pin, this two pin, then whatever the output is called as, whatever the configuration is called as non-inverting configuration of operational amplifier. What is it called? Non-inverting amplifier. Okay, so we'll see in detail. So non-inverting amplifier, what we will do? So this is the diagram. Here we are giving the input to the my inverting pin. This is minus is inverting and plus is non-inverting. So via one resistor Re, I have connected to the inverting pin, and from this I have connected a feedback. So this kind of feedback is called as negative feedback. Why? Because output portion is fed back to the input at inverting, that is minus pin over there. Okay, so normally in amplifier we are using the negative feedback, and in case of oscillator we are using positive feedback. So in case of this, you will always the circuit is of negative feedback, that is output, part of output is taken back and provided at the input at inverting pin. So this is the configuration. So V in, I have connected across this pin. I am giving input at this pin. Okay, input, and due to which a current cause to flow. As we know that resistor is there, the current is caused to flow. Okay, so this is my V2 and V1 voltage at inverting. But what will happen? V1 is connected to ground, so that's why V1 is equal to 0 over there. And whatever difference in between this V1 and V2 is called as V difference over there. Okay, and the output current cause to flow is called as I out over there, and output voltage is V out over there. Suppose if I want to calculate the current, that is nothing but the I. Where is the I? Okay, if I want to calculate the current, then what is the value of I? That is nothing but input voltage. Okay, this input voltage minus output voltage means voltage difference divided by total resistance. So that is nothing but R1 plus Rf. Okay, this is nothing but my I, total I cost of flow. This is total I. So that is nothing but the input voltage V in minus V out divided by R1 plus Rf. Okay, so or we can say that I, this is current, is nothing but V in. Okay, V in is nothing but my V in is here V in minus V2, this V2 divided by R in. So how I have calculated this thing? Because voltage is nothing but the voltage difference. So current is nothing but my voltage difference. So V in minus V2. Okay, just remember V in. This is my V in. Okay, minus V2 divided by R in. This is R in. That is the in source means starting voltage minus the end voltage divided by resistance. This is nothing but my I. Or we can say that. Or we can say that again. In this case, my I is nothing but what? IF. This IF is nothing but V2 minus V out divided by RF. V2 minus V out divided by RF. And all this current I am mentioning as same. Why is it so? Because we know that in the series configuration, current remains same. Current remains same because we know that input current is 0. So whatever the current I in is equal to my IF. So this overall current is same. So I is equal to IN is equal to IF. That's why I have mentioned that I over entire range. Okay, so from this I can say that I is equal to V in minus R in minus this is I'm writing. Okay, minus V2 by R in is equal to V2 by RF minus V out divided by RF. So I have written this. I have split it out this term, these two term, V in by R in, V2 by R in. I have splitted this term, splitted this term. Then so what will happen? So what will happen if I am taking the V in minus V in by R in? So this I will say, okay, this I will say is equal to V2. This will go in multiplication. Then if I'm taking the common of this, if I'm shifting this term to this side, then what will happen? This minus will get plus. So V2 divided by RF plus V2 by Rin minus V out divided by RF. Okay, and V2 I am taking common, then what will happen? 1 by Rin divided by 1 by RF. Here R is there. Okay, Rin is there. So from this term I can say that this term V2 is 0. So the V2 is 0. Why is it V2 is 0? By virtual ground concept. So what exactly mean by virtual ground concept? This V1, if I'm connected to ground, then this potential at this point is also equal to 0. This is nothing but by virtual ground concept. What is exactly mean by the voltage at this terminal? Voltage at this terminal is equal to voltage at this terminal is nothing but my virtual ground concept. Okay, then V2 is equal to 0. The overall term will be 0. Okay, overall term is 0. Then what is remaining? Minus V out by R in. Okay, so this is nothing but what? This is nothing but what? I is equal to V in divided by R in. V in divided by R in is equal to minus V out upon R. If I am cross multiplying this thing and calculate for voltage, that is nothing but the minus RF by R1 is equal to minus V out upon V in. So output by input is my gain. Okay, output my input is gain. So if I'm shifting the I'm multiplying with negative signal symbol, then negative, then minus RF upon R1 is equal to what? V out divided by V in. V out divided by V in. So the gain formula is nothing but what? Gain formula is nothing but minus RF upon R1. Keep in mind that whatever the gain is calculated by RF upon R1. My output is nothing but what? Gain into input. So minus RF upon R1 into V. That's why my output is of what? Inverting phase with my input. Inverting phase with my input. So what we'll do? We will design a circuit. So I'm having one simulation over here. So input voltage, if I'm putting the input voltage as 1 volt. Okay, 1 volt. Then R1 is of, I will say 1 kilo ohm, and RF I will put as 2. Okay, or 3, and input voltage is of 1 volt. Okay, so what we'll see here, the connection diagram is again remaining. So I will connect this thing to the ground. Yeah, I have connected this thing to the ground. Okay, then input voltage I will connect it to this resistor. This resistor connected to the this terminal. This feedback resistor I will connect over here, and this feedback resistor I will connect it to this side. So 1, okay, this 1, 3, 4. I have connected everything. Connected, and if I am putting, yeah, if I want to plot the waveform, then if I am changing the voltage, okay, just a minute, I will draw portion once again and I will draw for you guys. Okay, this is a simulation in which you can design your inverting amplifier and you can test your output. Test your output. So wait for a minute, I will go for you there. So input voltage is of 1 volt I will apply. Okay, then RF R1 I will use of 1k, 2k. RF is of 4k, I will add 4k. Okay, 4k, and I will connect these things. So V pin I will connect. Okay, this terminal connected, these two terminal are connected, this is also connected, this is of V out, this is of ground. Yeah, so here if my voltage is like this one, this is the waveform of this one. So this is the circuit diagram. I will show you in the next lecture how it will work. Some internet issues there. Okay, so this is nothing but my inverting amplifier. So in case of non-inverting amplifier, what we have to do, we have to connect my input to the non-inverting pin, that is nothing but the plus pin, and in second pin I have connected to the ground. The feedback I have always used the negative feedback, that is via RF resistor. This R2 is there. So if I am going for the current, that is nothing but the IF is directly connected to this current is going to flow, that is nothing but my feedback current is equal to I out over there, and input current is like this one, input via input current is flowing. So the V1 is equal to what? This voltage divider is nothing but R2 voltage across this terminal divided by voltage spreading as these two, that is nothing but the R2 divided by R1 plus RA into V out. We know that voltage division formula with the help of voltage division formula, and we know that by using voltage virtual ground concept, this V in is equal to V1. So I will write V1 is equal to V1. Okay, so V1 is equal to N. So from this one, V in is equal to R2 divided by R1 R2 plus RF into V out. As we have to find out the gain, so what we'll do, V out by V in I will calculate. So this two term, this will go, if I am cross multiplying, this will go to the numerator and this will go to denominator. So V out by V in is equal to R2 divided by RF. So if I am calculating further, so R2 by R2 plus RF by R2, so 1 plus R2 by RF by R2 is there. So my, this is nothing but my gain. So V out by V in is nothing but my gain, that is nothing but 1 plus RF upon R1. And if I am to calculate the output is nothing but 1 plus RF upon R2 into V in. So this is nothing but my output voltage. So from this we can observe that my gain in inverting amplifier is nothing but minus RF upon R1, and my output is nothing but minus RF upon R1 into V in. And the second case, in the non-inverting amplifier, my gain is nothing 1 plus RF upon R2, and output voltage is nothing but 1 plus RF upon R2 into V. That is nothing but gain into input voltage. So I think we have to stop over here. In the next lecture, we will see the simulation of this one. That is nothing practical of this one. So thank you very much for attending this lecture. Thank you.